If there is 23% of dark matter in the universe, then we can accept the possibility that the elementary particles known to us are not elementary, but are made up of some smaller substructures that we are not yet able to discover with current possibilities. Then we can think about fractal structures and use the same structural basis for models of photon, electron, positron, quark and other particles. According to string theory, the basic unit for the creation of higher structures could be an oscillating energy string in a closed toroidal space, in some quark-gluon plasma. Ring structures can be bound to each other by electromagnetic fields. The electric field between the rings acts as a repulsive force, while the magnetic field acts as an attractive force. For such a bound structure, we can determine the vector of the magnetic moment. The ring theory postulates that we perceive chains of ring substructures that form open structures as a wave, and we perceive substructures folded into closed ring structures as matter. We can model the photon as an open structure composed of oscillating ring substructures. Oscillations of substructures produce standing oscillations with the same amplitude but different phase. The phase shift of the oscillating substructures creates successive waves with free ends at which waves of the same phase are reflected. The photon structure modeled in this way is a half wave. Energy is transmitted by successive waves. The energy oscillates from front to back while simultaneously rotating around the longitudinal axis of the photon. For a photon modeled in this way, we can determine the direction of the photon's movement, which coincides with the direction of the magnetic moment, as well as the plane of circular polarization, which is perpendicular to the direction of the photon's movement. It is proven that electric and magnetic field intensities change simultaneously, and therefore the coordinates of points in space where the field intensity changes are functions of time. Ring theory offers a model of the electron as a dynamic toroid-shaped particle that is made up of multi-level composite ring substructures. These substructures are bound to each other by an electromagnetic field. Such a structure allows the proposed electron model to respond by changing the radius to a change in the binding energy or a change in excitation energy. A traveling wave, which originates on phase-shifted oscillating substructures, transmits energy at its peak, which we call a charge. Depending on the direction of rotation of the substructures and the direction of the phase shift, a positive or negative charge is defined. This structure is both a wave and a particle. According to de Broglie's hypothesis, it is possible to consider an electron as a wave from a wave point of view. In order for an electron to be stable, an integral number of wavelengths of one electron must be stored in the electron's path. The de Broglie wavelength of an electron is based on the relation lambda is equal to Planck's constant divided by the mass of the electron times the speed of the electron. According to the Rutherford model, we express the speed of the electron v, and by combining the two formulas, we obtain the relation for the wavelength of the electron lambda. By substituting the basic constants, we obtain the wavelength of the de Broglie wave of the hydrogen electron, which is equal to 33 whole times 10 to the minus 11th of a meter. The ring theory assumes that the electron is actually a closed photon. Therefore, the electron at the fundamental level is made up of a closed half-wave. Therefore, when two photons collide, an electron and a positron with opposite spin can be created. At the second energy level, the electron is made up of two half-waves. At the third level it is made up of three half-waves, and so on. Since ring theory works with a model of the electron as a toroid-shaped dynamical particle that is made up of multi-level composite ring substructures, the questions will arise: how big is a free electron? What is the proton and electron configuration of a hydrogen atom? What is the radius of a bound electron in the ground state of a hydrogen atom? Is the radius of the electron related to the wavelength of the ionizing photon? What is the energy of an electron of a hydrogen atom in its ground state? How does the radius of an electron change during excitation? How is the radius of the electron related to the wavelength of the excitation photon? What is the distance between a proton and an electron on a common axis? How does the distance between the proton and the electron on the common axis change during excitation? What kind of energy does a photon transfer to an electron? Does the mass of an electron change during the absorption and emission of photons? We will try to answer some of these questions in the following text. The size of the radius of the electron model of the hydrogen atom at the basic energy level is based on the terms of individual series of spectral lines. The Lyman series term is 91.2 nanometers. The term of the Balmer series is 364.6 nanometers and the Paschen series term is 820.4 nanometers. We calculate the electron radius of a hydrogen atom at the base level according to the formula term times constant alpha divided by 2 squared times 2 pi times n squared, where n is the energy level of the individual series of spectral lines. After substituting the values, we get the calculated size of the radius of the hydrogen electron model R at the first energy level of 2.65 times 10 to the minus 11 meters. The size of the electron radius calculated in this way corresponds to the experimentally measured value. Since energy moves around the electron circuit 137 times slower than the speed of light, the recalculated wavelength of the lambda electron is 22 full 808 nanometers. The internal energy of the electron, including the energy of the substructures, is 54 whole 394 electron volts. A quarter of this energy is identical to the binding energy of an electron of a hydrogen atom at the ground level. An important role for explaining the structure of the hydrogen atom, according to the ring theory, is played by the magnetic moments of elementary particles. Currently, the magnetic moments of the proton, neutron and electron have been experimentally proven and very precisely measured. What does the magnetic moment tell us about the elementary parts? We know from physics that the magnetic moment of a planar conducting loop of area content S, flowing through a constant electric current I, is equal to the product of the current and the area and is oriented in the direction normal to the area according to Ampere's right-hand rule. So if the elementary particles, proton, neutron and electron, have an experimentally measured magnetic moment, then we can hypothesize that all these elementary particles have the same structure similar to a current loop, where the current is created by the movement of the charge along the ring, or toroid. For the proton and neutron, ring theory works with the hypothesis that three quark particles always define a plane. If there is an exchange of energy between these particles, for example by the movement of charges in one direction, then we can also associate this event with an electric current in a closed current loop, and we can apply the known physical laws of electromagnetism to it. To define the magnetic moment, it is necessary to know the radius of these particles. However, this was experimentally measured only for the proton. However, we can make the assumption that the radius of the neutron will be very close to the radius of the proton. According to the ring theory, we can calculate the radius of the binding electron of a certain element using the wavelength of the photon of its term. The magnetic moment vector of a multi-level structure is defined by the direction of rotation of the substructures and the direction of the charge movement along the outer circumference. For an electron with a negative charge, the direction of the magnetic moment vector is determined according to Ampere's right-hand rule. For a positive charge, the left-hand rule applies. The direction of the magnetic moment for the proton and neutron is the same as the rule for the positron. In quantum mechanics, the existence of a physical magnetic moment has been replaced by a mathematically defined spin. Regarding the magnetic moment of the electron, among the physical constants of particles we find the so-called Bohr magneton, which presents the orbital magnetic moment of the electron of the hydrogen atom and is derived from the orbital moment of momentum of the electron of the Bohr model of the hydrogen atom with a radius of 5 whole 29 times 10 to the minus 11 meters. But in 1913, when the Danish physicist Niels Bohr derived this relationship for the orbital magnetic moment, neither the proton, nor the proton's magnetic moment, nor the electron's own internal magnetic moment were yet known. It was experimentally measured only in 1923. It is interesting that its magnitude is almost identical to the orbital magnetic moment of the Bohr magneton. The proton's magnetic moment was experimentally measured much later, in 1952. If, in the case of the Bohr model of the hydrogen atom, we calculated the interaction of the magnetic moments between the proton and the electron, in the case of their parallel vectors, the size of the radius of the electron's path would be greater, and in the case of the antiparallel direction of their vectors, the distance would be smaller, and the given Bohr radius would not be a physical constant. Even in 1925, when the Schrödinger equation was created, the proton's magnetic moment was not yet known. Therefore, even in this equation, the magnetic field of elementary particles, their magnetic energy, or the magnetic interaction of elementary particles, which is as strong as the electrostatic interaction, is not taken into account. Most quantum mechanical calculations involve only the electrostatic interactions between electrons and the nucleus and between electrons. But where has the magnetic energy presented by the magnetic moments of elementary particles gone? Can this theory be correct without the existence of magnetic moments of elementary particles? However, if we break away from Bohr's model of a hydrogen atom with a point electron freely orbiting around a positive proton, and we replace it with a ring model of a proton, and we replace a point electron with a model of an electron with a ring multilevel structure according to the ring theory, along the circumference of which the electric charge moves, then there will be significant changes in the relations between the proton and the electron. In Bohr's model, as the distance between the proton and the electron decreases, the magnitude of the electrostatic force increases exponentially inversely proportional to the distance to infinity according to Coulomb's law. On the other hand, in the ring model, when the distance between the proton and the electron on the common axis decreases, the electrostatic force in the axis of the rings, after an initial increase, decreases to zero. The size of the electrostatic force is affected by the size of the electron radius. If we associate a proton with a current loop, then by applying the Biot-Savart law, we can determine the magnitude of the magnetic induction at the point P, located outside the axis of the ring. If this point is located on the ring of the electron model, then the inhomogeneous magnetic field of the proton will exert a force on the current loop of the electron. The size of this magnetic force in the axis of both rings can be expressed using the modified Biot-Savart law. If the vectors of their magnetic moments are antiparallel, then the force between them will be repulsive. So if we use the laws of physics for the attractive electrostatic and repulsive magnetic force between the ring models of the proton and the electron, we can create a model of the hydrogen atom based on the balance of electromagnetic forces. Although the hydrogen atom is an atypical element, we can use it to show the calculation of electromagnetic forces, the calculation of the distance between an electron and a proton, and the calculation of the bond energy between a proton and an electron, which we will need when calculating covalent bonds. Ring theory presents a model of the hydrogen atom as a system of a ring proton and a ring electron on a common axis, so that the rotational speeds of their charges are not inhibited by their magnetic fields. The direction of rotation of the charges must be the same. If the direction of rotation of their charges is the same, then the vectors of their magnetic moments are antiparallel to each other, and therefore the magnetic force between the proton and the electron is repulsive. With the same direction of charge rotation, the directions of the magnetic moment vectors in the hydrogen atom can be antiparallel in two variants. A proton and an electron are kept on a common axis at a distance d in dynamic equilibrium by an attractive electric force and a repulsive magnetic force. We calculate the electric force in the axis of the rings using Coulomb's law and the magnetic force according to the Biot-Savart law. In these equations we express the transpose r and the sine and cosine functions using the values of r and d. Since in the ring structure of the electron, the movement of the charge is not tied to the rotation of its structure, there is no need to take into account any kinetic energy, nor the mass of the electron. To calculate these forces, we need to know the electron radius r and the electron current I. The size of the radius of the electron model of the hydrogen atom at the basic energy level is based on the terms of individual series of spectral lines. We calculate the electron radius of a hydrogen atom at the base level according to the formula term times constant alpha divided by 2 squared times 2 pi times n squared, where n is the energy level of the individual series of spectral lines. After substituting the values, we get the calculated size of the radius of the hydrogen electron model R at the first energy level of 2.65 times 10 to the minus 11 meters. The magnitude of the radius of the electron calculated in this way corresponds to the experimentally measured value of the radius of the hydrogen atom. We can also calculate the value of the electron current, which we need to calculate the magnetic force. From the modified relations for the equilibrium state between the electric and magnetic force, we get the relation for calculating the distance d on the common axis. After substituting the constants and the previously calculated values, we get the value of the distance between the proton and the electron at the basic energy level of the hydrogen atom in the value of 2^34 times 10 to the minus 11 meters. This value corresponds to the experimentally measured values of the size of the hydrogen atom. According to the ring theory, the model of the hydrogen atom in the ground state is formed by a ring structure of proton and electron on a common axis, at a distance of dynamic balance of electrostatic and magnetic forces. In the graphical representation of the equations for the electric and magnetic force on the common x-axis, we see that at a distance greater than the equilibrium position, the action of the attractive electric force prevails, while at a distance smaller than the equilibrium position, the action of the repulsive magnetic force prevails, which returns the electron to the equilibrium position. This property of electromagnetic forces allows dynamic equilibrium to be maintained around the distance d. From the y-axis force graph, we see that at a distance greater than the radius of the electron, the attractive magnetic force helps the attractive electric force to decrease the radius of the electron. At a distance smaller than the radius of the electron, the magnetic force already acts repulsively with a tendency to increase the radius of the electron. From the relations for the calculation of electromagnetic forces, we can express the relations for the calculation of electric and magnetic energy in the x-axis. From the graphs of these equations, it can be seen that at the distance of the balance of forces there is no balance between the energies, but the magnetic energy has a greater value than the electrical energy. The difference between the energy of the electric field and the energy of the magnetic field in the x-axis at the point of balance of forces gives the value of the energy that we must supply to this system in order to separate the proton from the electron. We call this value the binding energy. For a hydrogen atom at the basic energy level, the binding energy is equal to the ionization energy. The importance of spectral lines is not only in determining the energy of a photon. From the spectral lines we can obtain information about the radius of the electron and its circumference, but also about the photon's own size and the distance between the proton and the electron. The table shows the values from the database of photon wavelength spectra during the transition between adjacent energy levels of the hydrogen atom. From these photon wavelengths, the radii of the electrons at the individual n levels are calculated. The following columns show the calculated values of the radius differences between individual levels, the circumference of the electron and its increments, the photon energy, and the levitation distance between the proton and the electron on the common axis. The wavelength of photons between the n and n+1 levels increases exponentially with the increase of the principal quantum number n when the electron of the hydrogen atom is excited by 1 degree each time. The wavelength of photons is determined experimentally and its value is found in the NIST spectral line database. The photon energy between the n and n+1 levels decreases exponentially. The radius of the electron increases linearly with the increase of the main quantum number n when the electron of the hydrogen atom is excited by 1 degree at a time. Since both the electron and the photon are made up of dynamically connected substructures, At the beginning of the table and the graph you can see the strong deformation effect of the components of the proton's electromagnetic force vectors, which point to the center of the electron's ring and thereby reduce its radius. The increase in the radius of the electron is finitely close to the value of 5-297, which corresponds to twice the radius of the electron in the ground state according to the ring theory. The circuit of the electron grows linearly with the increase of the main quantum number n when the electron of the hydrogen atom is excited by 1 degree at a time. The increment of the electron's circumference is limitatively close to the value of 33(27). So we can agree with de Broglie's hypothesis that when an electron is excited to the north higher energy level, the fundamental wavelength of the electron increases n times. However, this magnitude is greatly affected by the electric and magnetic strength of the proton at the lowest values of the electron quantum number n, as documented by the magnitude of photon wavelengths from the spectrum table and database. We can hypothesize that with a constant increase in the electron circuit, there is a constant increase in the number of substructures in the electron circuit. This would mean that even the excitation photon between levels has the same number of substructures even at different photon wavelengths. The consequence of this hypothesis would also be an increase in the mass of the electron by individual levels up to the final experimentally determined mass of the free electron. From the graph of the distance of the electron from the proton of the model of the hydrogen atom, it can be seen that as the quantum number n increases and the radius of the electron model increases, the distance increases up to the 8th energy level n. As the radius of the electron increases further, the magnetic repulsive force decreases faster than the attractive electric force, and the distance of the electron from the proton on their common axis decreases when the planes of their rings are compared. This state allows the proton and electron to change the orientation of their magnetic moment vectors relative to each other using the minimum photon energy in the hydrogen spectrum known as the hydrogen line at wavelength 21 1 cm. The deuterium atom can be considered an isotope of the hydrogen atom, enriched in the nucleus by 1 neutron. Since the ionization energy of deuterium is almost identical to that of a hydrogen atom, we can also use the same radius of an electron as for a hydrogen atom. In the deuteron model, the addition of a neutron does not change the magnitude of the electric force, but the combination of the magnetic moments of the proton and neutron doubles the magnitude of the magnetic force. The equation for expressing the balance of forces will have the form. After analyzing the equation, the dynamic equilibrium state yields the distance of the electron from the proton and thus the atomic radius of deuterium to be 4^2 × 10⁻11 meters. To build a model of a tritium atom, we will use the same approach as for the deuterium model, with the addition of an additional neutron. The magnetic force will be 3 times greater than that of a hydrogen atom. The resulting distance for the equilibrium state and radius of the tritium atom model is 5^5 × 10⁻11 meters. The wavelength of the photons allows us to calculate the size of the radius of the electron, which is further needed to calculate the bond length and the binding energy between atoms in molecules. Since the ionization energy of photons is different for individual atoms, the size of electrons at the ground level and other energy levels are also different. But more on that in the next presentation. Thank you for your attention and open mind.